Hello, my dear students, and welcome to our screencast for Virtual Monday. We will be discussing the laws governing formulas and names. This is our last topic before we have a test. I'm scheduling a test for Friday. And I'd also like you to remember that tomorrow, Tuesday, is Parent-Teacher Conference Day, and we will have early release that day. I'll try to plan nothing but labs and reviews for the remainder of the week. So if you go to your Google Classroom and you go to your classroom stream, you'll find a post with attachments for all the notes. There are 5 of them. And this is the one governing laws, or laws governing writing formulas and names, and there are things you can do and that I can do to make it so I can view it in an appropriate program. I want to say I need to go to share and export after I open it up in a new window, and I need to send a copy of the file to my files, or in this case I can go straight to Keynote. I usually save it in files, but I'll go straight to Keynote, and we can quickly go through this material, which is just a quick summary of the 2 rules originally proposed by John Dalton, who we've met before, an English chemist from long ago. But in fact, one of them was called Dalton's Law of Definite Proportions. But a birthday cake, in this example here, for a 4-year-old has 4 candles. And what we're talking about are ratios, how we use these ratios to describe and define different compounds, both ionic and molecular. And for a 4-year-old, there'll be 4 candles for every 1 cake. And we have similar relationships when we talk about our different compounds, the different molecular compounds and ionic compounds. Now, there are 2 laws that kind of describe how compounds form, and they're fundamental to all of chemistry. You may think they're rather obvious, but think about the times when these laws were first proposed. It wasn't so obvious. We didn't have the uniform naming, the uniform analysis, and the consistent analysis of compounds that we have today. So the 2 laws are the law of definite proportions and the law of multiple proportions. And the law of definite proportions we'll do first. It says that for any chemical compound, the masses of the elements are always in the same proportions. And it doesn't matter where you are. If I have a sample of sodium chloride, it doesn't matter whether I'm in the United States or in China or in Africa, in any sort of part of the world, when we have what we agree to in the International Union of Pure and Applied Chemistry that controls naming and formulas and units and measurements as well, but in this case, naming and formulas, when we say sodium chloride, it means the same thing all around the world. And the law of definite proportion, again, says that, that for any chemical compound, the masses are always in the same proportions. And a good example is water and hydrogen. The ratio of oxygen to hydrogen is always 8-to-1 because oxygen has a mass of 16, 15.99997 or something like that, but it basically is 16, and hydrogen has a mass of 1. I know it's 1.0017 or something like that, but for our practical purposes, there are 2 hydrogens each with a mass of 1 for a total mass of 2, and oxygen has a mass of 16, so the ratio is 8 to 1. And if you look at another compound like hydrogen peroxide, and wherever you are in the world, it's the same. You have 2 oxygens at 16 each, so that's 32. And you have 2 hydrogens at 1 each, so that's 2. So the ratios 32 to 2 are simplified to 16 to 1. That's it. It's as obvious as that. The law of multiple proportion states that when 2 elements form more than one compound, the different masses of one element that combine with the same mass of the element are in the ratio of small whole numbers. An example of this might be nitrate and nitrite, or carbon monoxide and carbon dioxide, or the previous example of water and hydrogen peroxide. This actual slide has an error in it. We've got the ratio of compound A to B is what? 5 to 2, or 5 to 1, and in the next one, the ratio of A to B is 10 to 2, which is also 5 to 1. But when you add in a third element, it's 7 grams and 12 grams. But again, small whole number ratios. We can treat this mathematically. And here's a bit of an example, but you have 2 compounds. Compound A has 2.41 grams of carbon, and compound B has 6.71 grams of carbon. Sorry, let me go back. If I can go back, I'm having trouble going back. It's only taking me forward. See if I can go back. There we go. And compound A has 3.22 grams of oxygen for every 2.41 grams of carbon. Compound B has a different ratio, 6.71 for 17.9 grams of oxygen. And this is something we do more in advanced chemistry courses, or maybe AP chemistry. You want to calculate the lowest whole number ratio of carbon in these 2 compounds that combines with a given mass of oxygen. And what you do is you do a little cross multiplication, and you solve each of them for how much carbon would combine with 1 gram of oxygen in each case. And if that is the case, if you'll look at this example here, well, let me see if I can make this so that, well, we can't look at both of them at the same time. But in this case here, where we had 2.41 grams of carbon per 3.22 grams of oxygen, if I were to put that to equal a ratio of X grams of carbon per 1 gram of oxygen, cross multiply and solve for X, I would get that X is equal to 0.748 grams of carbon, as shown in the top numerator in the first equation for compound A. And if I do the same thing, the second compound has 6.7 grams of carbon per 17.9 grams of oxygen. And if I were to find out how many grams of carbon in this compound per 1 gram of oxygen, I would set that X over 1 gram of oxygen, cross multiply, solve for X, and I would get 0.357 grams of carbon. So now I have these 2 values, 0.748 and 0.375, and I look at the ratio of those 2 values, and I see that it's 2 to 1. And what this says is that compound A simply has twice as much carbon per gram of oxygen as compound B. So that's a small whole number ratio, 2 to 1. But we're not going to work these mathematical problems. We'll get mathematical enough in a little bit, in a short while in the course, as we start looking at more quantitative aspects of chemistry. But right now, understanding the properties of covalent and ionic compounds and understanding how to name them and write their formulas is most important for us. So we won't work another problem, but for those of you who want a quick review, and that really does it for laws governing formulas and names, and for those of you who are very visual, it is, they do have flow charts for solving these problems for writing formulas given the name, or for writing the name given the formula. And so, if you want to write the name, you just look at this flowchart and you ask certain questions. So this is a compound QR, and we don't know how many of each are there, but it doesn't really matter. But if Q is an H, well, now it's an acid. If my cation is an H plus, it is an acid. The example given here is nitric acid. And then if we go on and ask, is it 2 elements or more than 2 elements? If it's 2 elements, well, the question is it more than 2 elements? If the question is no, it must be 2 elements. It's a binary compound, and its name is going to end in "ide." And staying on the left side, if the Q, the cation, is a metal, let's say it's not, then it's a molecular compound. If it's not a metal, it can't be a metal salt. So it must be a molecular covalent compound. And you use prefixes in the name, the Greek prefixes for the number of each type of atom present. If it is a metal, then you have a group A name like sodium chloride, barium sulfide, calcium oxide. But if it's a group B metal, if it's not a group A, then you have to use the Roman numerals, because those group B metals have multiple valences. The group A, the valence is obvious. It's equal to the group number. And for the B, they can have multiple valences. So, for example, the example given is iron 2 chloride. There's also an iron 3 chloride, because iron exists as both +2 and +3. So going back up to the top right, if you have more than 2 elements, it must be one of the aspects of the compound must be a polyatomic ion. And if it's with a group A, you just name the ions. Lithium carbonate is the example given in the green arrow, yes. But again, if it's a group B metal, for this time copper, copper can exist as +1 or +2. In this case, it's copper 2 sulfate. SO4 2 minus is the sulfate anion, and I will give you a chart of the anions when we take a test. So if you're a flow chart and a visual person, that's what you need. Here's copper sulfate from the flow chart. It's a very interesting compound. In the bottom, you see it is white, but when it's exposed to water, it turns blue. And a little piece of adhesive with some copper sulfate in it is on the inside of your phone. This is how they know you dropped it into water, because it starts out white, and if you take your phone in to be repaired and they open up the back and see that it has turned blue, they know that your phone was exposed to water. It's a little tag in there that is a nice indicator of water. So if you're into guidelines, they say there are 4 guidelines. I never really stopped to count them. I just remember all the guidelines or rules for writing the formula. If it ends in "ide," it's a binary compound like sodium chloride is the best example. If it ends in "ate" or "ite," it's a polyatomic ion like sodium nitrate or sodium nitrite, sodium sulfate, sodium carbonate. Those are polyatomic ions, and of course you'll have a chart of the polyatomic ions. If you have prefixes, carbon dioxide, not carbon oxide, carbon dioxide, carbon monoxide, phosphorus pentachloride. If you have those Greek prefixes for the numbers, the compound is molecular or covalent. It's not an ionic compound. And if you have a Roman numeral, it means it's made with a group B transition metal, because they have multiple valences, and we have an old system where we named them separate, as in ferrous and ferric, but now we just say iron 2 and iron 3. And it's beautiful because when you say iron 3, you know the charge on the iron is 3 plus 3. The Roman numeral gives you the charge on the metal. You can also use a flow chart if you're visual and you want to think about how you're going to name chemical compounds. You can use a flow chart like this one here. Does it have prefixes? If it does, it's a molecular compound. If it doesn't, it's ionic. And if it's a group A metal, the group number equals the charge for the metals, and then for the non-metals, it's, of course, -8, the group number -8 to get the charge. If it's a group B metal, you use Roman numerals. And polyatomic ions, you're going to have a table of the polyatomic ions so you know what you're dealing with. It will be included in any test or questions or assignments. And the main thing to do is to balance charges. Use the crisscross method. A good example is lead 2 phosphate. Lead 2 has a +2 charge. Phosphate has a -3. You have to kind of cross multiply. 2 times 3 is 6. So you're going to need 3 plus 2 leads and 2 minus 3 phosphates so that you have a -6 and a +6 total that balance out to give you your neutral compound. So, the law of definite proportion states that samples of any chemical compound, the elements are always in the same proportion by mass, okay? And that's the answer, mass. And if you want to write the chemical formula for iron 2 chloride, based on figure 9.2, after identifying symbols, what's the next correct step? It's looking for those Roman numerals. That's a dumb question. I wouldn't give you a flow chart and ask you what the next step is. I would just expect you to be able to name the elements and pick them out. Thank goodness it's multiple choice, right? Pick them out from a selection. And if a molecule ends in -ite or -ate, then a polyatomic anion is involved, as in sulfate or nitrate or chlorate, all those common anions. So let's quickly go back and look at our assignment. So I can't really go back to slides, but I can go back here to our Google Classroom and close that down and go to classwork. I'm opening up classwork here at the bottom, and a new assignment for Monday, for Virtual Monday, has been posted. And here it is, and it looks like this. If you save it and, well, open in a new window first, and then you can open in a different program. And what I've done is open it in a program that allows me to edit my PDF. And if I can find it, I will do so. And here is your homework. I will just quickly go through it from a review standpoint. You can do a screenshot or open up yours and start using my answers as you wish. Anyway, the law of definite proportions, number 1 is definite proportions, states that samples of any chemical compound, the masses of the elements are always in the same 2 proportions. So 2 is proportions. The law of multiple proportions, that would be 3, multiple proportions, states that whenever the same 2 elements form more than one compound, the different masses of one element that combine with the same mass of the other element are in the ratio of small whole numbers. Now this next one, H3PO4 is an acid. So number 5 is acid. It is called phosphoric acid. It's one of those acids we saw on a table. The fact that it has an H in it is what gives you the clue that it is an acid. CCl4 is not an acid. That's kind of a dumb question, and you would never get a question like that from me. But it contains two elements, so it is a binary compound, and that is a legitimate question. It does not contain a metal, so it is a binary molecular compound with purely covalent bonds in it, no ionic bonding. And this compound is called carbon, and here's your Greek prefix, tetrachloride. Tetra meaning four. For number 10, carbon tetrachloride. The next one has Pb, parenthetically, C2H3O2 times 2, that whole quantity times 2. And that C2H3O2 minus 1 is the acetate anion. And it is not an acid because it doesn't have H. It contains more than two elements. And here is that polyatomic anion. So number 12 is elements, more than two elements. So the C2H3O2 minus, 1 minus, is a polyatomic ion or anion. Either answer is fine there. I put anion. And Pb is a group 4a metal. And it can exist as a +2 or a +4. In this case, it has two acetates, -1 each. So the lead must be +2 to balance the -2 charge overall. And so this compound is called, as you see there, lead 2 acetate. Now I'm going to quickly move on to our conditional true-false. And Roman numerals are used when naming group B metal cations. And I don't know how to answer this, because if I see a Roman numeral, I know it's a group B transition metal. Always. But there are a couple of transition metals that don't have multiple valences. The one I think of all the time is silver. It's always +1. Okay? So I guess you don't need a Roman numeral. If you put silver Roman numeral 1, nobody would say anything, except you'd be wasting your time. So I guess it could be sometimes true from that standpoint. It's not a very good question, because I don't like, being able to give different answers depending on how I interpret it. Number 17 says, names of compounds contain polyatomic ions and an "ide." Well, rarely, but especially if they have a polyatomic cation like ammonium, you could have ammonium chloride or ammonium bromide. And so that's sometimes true. Prefixes or prefaces are used when naming binary ionic compounds, and that's never true. Prefixes are used when naming binary molecular compounds. Ionic compounds never use the prefixes, because we can calculate it and figure it out from the charge. I don't know why that line is not moving. There we go. So, and finally, compounds containing two elements are called binary compounds. Absolutely, that's always true. So let me, down here at the bottom, show you how I'm going to name the following compounds. This is lead. It's a transition metal, lead 4 acetate. And this time it has 4 acetates. Up in the example in the fill in the blank, it was lead 2 acetate. So there's the Roman numeral 4. It's 4 minus 1 acetates. Again, you'll have a chart of the polyatomic ions. HF is hydrogen fluoride. However, notice that H there. If you put this into water, it forms hydrofluoric acid. So I could take either answer there. They are basically the same compound, just depending on conditions that change it from an ionic compound to an acid. The next one is P2O5, both nonmetals, so it's diphosphorus pentoxide. You have to use your Greek prefixes. And finally, a simple ionic compound, lithium, which is group 1 and +1, bromide, which is group 7 and -1. So you don't need any subscripts. It's simple lithium bromide. And now, going in the other direction, write the formulas for the following compounds. So can you interpret this? And remember, when you see these questions, they are going to be multiple choice, and you won't actually have to name them. You'll have to pick the correct name. That might be a little easier, I hope. Anyway, for 21A, phosphorus pentachloride is PCl5. I cannot type subscripts in here. I need to be in a better word processing program like Microsoft Word to be able to write subscripts. But that 5 should be a subscript 5. Iron 2 oxide. Well, iron 2 means +2, and oxygen always forms a -2 anion. So it would be a 1-to-1, +2 and -2, 1-to-1 ratio, FeO. And by the way, that's what we call rust. Next would be nitric acid. So this is an acid, so I need an H. And the nitrate, because the 8 salt becomes the ic acid. So this is nitric acid. That is a hard one, I admit, remembering all the acids and the rules for acids. Potassium chloride is a simple ionic substance of a metal plus a nonmetal. Potassium is group 1, it's always +1. Chloride is group 7, it's a halogen, and it's always -1. So a +1 and -1 are going to be present in a 1-to-1 ratio. And finally, calcium nitrate. And calcium is group 2, it's always +2. Nitrate is a polyatomic anion equal to -1. So I'm going to need 2 of them to balance the +2 of the calcium. And we put parentheses around that polyatomic ion indicating they stay together. That's your assignment for Monday, Virtual Monday. We will do